Hi everyone, welcome to the 33rd webinar in 12D's training webinar series. My name is Lisa Stewart and I'm the Marketing and Communications Coordinator at 12D Solutions. While we wait for everyone to finish joining and get comfortable, I'll launch a polling question. You'll have about 30 seconds to answer about the source of your inlet capacity equations, and then I'll show the results. Okay, so it looks like a lot of people have them supplied by a local road authority, but there's quite an even mix of attendees here. Welcome everyone. Okay, let's get started. 12D's training webinars showcase common industry challenges, taking a close look at industry best practices and how these can be implemented using 12D products. The aim of these webinars is to upskill 12D users and broaden their understanding of the capabilities of 12D products. We run these webinars regularly and record them for posting through our website and on YouTube. The first 32 webinars from this training series, as well as the 29 webinars from our Industry Solutions series, are available on our YouTube channels if you missed those. During this live presentation, you'll be able to type your questions along the way. We'll put some instructions on the screen. We'll answer as many as possible of those throughout the webinar, and at the end I'll read out some of the questions to the presenter for his insights if there's time. Today's webinar, Inlet Capacity, SAG and On-Grade Locations, will be presented by Rob Graham, our resident water resources engineer. With almost 20 years of experience here at 12D and over 30 years of experience in the industry. Urban stormwater systems convey water via surface flow and underground pipe systems. A critical link between the two systems is the stormwater inlet and its flow capacity. 12D model stormwater hydraulics inlet capacity calculations are available for the rational method peak flows and the unsteady flow, using either 1D or 2D, two-flow, overland flow hydraulics. This webinar will discuss modelling using these three cases for SAG and on-grade inlets. Details will include entering inlet curves into the drainage.4D, on-grade inlet curve selection, inlet blockage, side-by-side inlets, and surcharging inlets. Over to you, Rob.
Thank you very much, Lisa. Good afternoon, everyone. Today we're going to look at inlet capacities. And inlet capacities, as Lisa mentioned, are a fundamental part of having a dual hydraulic grade line system. When we are looking at our nodes inside 12D, we have manholes, sags, and on-grade inlets. And when we look at these today, we're going to look at the uncaptured flow. That is the water that cannot make it into the inlet. And that will be in contrast to surcharging flows, which is what result when the hydraulic grade line in the subsurface is too great and pushes water back out to the surface. It's just a matter of time. We will definitely focus on the inlet capacity and uncaptured flows. When we start doing this analysis, it becomes important to have inlet capacity curves. We'll talk more detail about these curves, but they generally come from manuals or formulas such as those available in HEC 22, or even better, in my opinion, when they come from hydraulic laboratory testing. We're going to look at the Drainage Network Editor, really the heart of 12D's hydraulics and hydrology, and see how that interacts with our drainage.4D file. That's our database where we enter all of our inlet capacity curves. Once we get this background information all sorted, we're going to look at how this is implemented in 1D, 2D modeling, and with the rational peak flows. And finally, we'll end off looking at some inlet blockage. So let's start with why inlet capacity is important. Whenever stormwater cannot make it into a pipe system, it remains on the surface, and that can create and will at some time create an unsafe environment. Safety is, in my opinion, probably the most crucial part of stormwater design. The second part, of course, is serviceability and access. If we need access to critical services, and of course we want to be able to use our roadways and that sort of things when it's raining, we need to use these a little more frequently. And for that, we need the pipe systems and the inlet capacities. Now, I'd like to conclude just a short introduction part to say that storms will occur that will create an unsafe environment, and we will get cut off from critical areas. And what we need to do is get some sort of estimate of how often and how long and how long this cutoff will happen. So keep in mind that no matter what we do, we will still have unsafe environments. We're just trying to make the safety last longer. So let's take a look at those three node types that we described. We've got a few images here. The first one on the left is what 12D means by a manhole. You'll notice that it's got a sealed cover on it. No water can come in, no water can come out. And because of that, we won't let you attach a catchment to that. It wouldn't make much sense because no water could get into it. And the second thing, of course, is that if we have it in a bypass system, the bypass will just completely ignore it. So when we say a manhole, that's what we mean by a manhole when we refer to manhole, on grade, and sag. The second image you can see across is an image from a hydraulics laboratory testing facility at the University of South Australia. And what you see here is a sag inlet. And you can see the water quite slowly and evenly moving into the sag inlet. And what's unique about the sag inlets, it's generally the depth of water that determines how much is going to flow into that inlet. Now, when you move across to the third image, that's an on-grade pit. And just by looking at the flow regime that you see going past there, you'll see a hydraulic jump down at the end. You will see a very fast-moving flow as it tries to get into the grate. You'll partially see the effect of momentum and the velocities as the water tries to turn the corner to get into the inlet. So you'll see there's a great many variables that determine just how much water can get into an on-grade pit. The last image we see on the right is another sag pit, and this one, of course, is without the water, just to give you an idea of what they look like when they're not inside a roadway. So throughout the presentation, we're going to be talking about those three different inlet types. Now let's take a quick look as we jump across into 12D, where when we do our modeling, we get to specify what the inlet configuration is. And this involves two different, primarily the drainage network editor, but also the drainage.4D file. So let's jump across into 12D and see how this comes together. So we're going to be looking at a very small network today because it's a training session. And you'll notice that we have a few inlets here. We've got a couple of them are sags, a few of them are on grades, and the water eventually comes out the head wall down here at the end. So where I want to take you first of all was to our drainage network editor. Now, if you're unfamiliar with using the toolbars and you find your way to the 12D track, you'll find that the drainage network editor is the button underneath the track. So the first thing we'll do is we'll come across and we'll go and pick one of our inlets. Now, one of the first things I might mention is that when we decide whether a pit is an on-grade or a sag pit, sag inlet, it's a very important decision. Sag inlets tend to capture a lot more water than an on-grade, and we must make a decision about whether or not it's truly acting as a sag. So when you make that decision, look at the slope of the roadway that comes into your inlet. Make a decision if you think that the water will truly almost stop, pond at that location, and flow in. And if it meets that criteria, it's pretty safe to say it will act as a sag inlet. If the water is going to continue on by, then reconsider that and start thinking about an on-grade. So let's move back to this first one, which is definitely an on-grade inlet. So we'll go pick that one. And let's move across to the pit tab. And on the pit tab, down here under inlet configuration, we get to select whether it's an on-grade, sag, or manhole. And in this case, you'll notice we are locked out. Now that's because the drainage network editor works very closely together with the drainage.4D file. And the way it's set up right now is that if the user was to come back, and if you were to select a sag road pit, it would come back with a bit of warning telling you that the inlet type is going to change. And if I say go ahead and update it, you'll notice that the inlet configuration has switched over to a sag pit. So the pit type has been uniquely associated with a certain inlet configuration. Now it doesn't have to be done that way, but it often is. So if I switch back again, I'm back to my on-grade pit. So you'll notice how they truly are linked together. Now let's take a moment and see how that linkage works. To do that, we'll move up to our design, come down to our drainage sewer, and move down to our drainage 4D editor. Now this editor is new to version 12, so if you're in one of our older versions, it'd be one of the many good reasons to upgrade. If we come across right now, I've taken a copy of my drainage.4d file and it's sitting in my user folder. And it's not write protected, so therefore I can, in edit mode, and selecting it, I can start editing that file. So let's move down and take a closer look at this road pit. So if I go select the road pit on the tree, and I scroll down just a little bit on my properties, you'll see that in here, the inlet type has been selected to be only on grade. It's this selection here that forces this inlet configuration to be locked to on grade. If I was to release this, then the user would be free to put in their own inlet configuration type there. I also mentioned before that when I switched over to the SAG inlet, that switched over. So let's go take a look at that one. There's the SAG road pit that I selected earlier, that type. And if we were to move down, we would find that that one also would be set to be a SAG. And of course, the other option is we could have that locked into being a manhole. So hopefully now I've made it apparent how the drainage.4d file can work together with the drainage network editor to make the whole use and modeling a little more accurate and easier to use, or consistent anyway. So that's the relationship between the drainage network editor and the drainage.4d file. Now let's start talking about inlet capacity calculations. The heart of the calculations are inlet capacity curves. And there's two primary sources, I would say, for these. There may be more. And the first is an excellent manual. It's put out by the Federal Highway Administration in the United States, and it's referred to as the HEC 22 manual. And inside this manual, you will find many descriptions of inlet capacities. It's chapter 4.4 that discusses inlet capacity, and you'll find a great number of equations for determining both inlet capacities for side inlets and for graded inlets. Keep in mind they are theoretical calculations, but it is definitely a start. There's many programs and spreadsheets that I've seen over the years that will implement these calculations. When you do go through the calculations, the general steps that you'll go through is starting off with a road crossfall. And inside 12D, we work with our on-grade inlet capacity curves in groups of constant crossfall. And you'll see these sets a little bit more in a few minutes. The next thing you would do is you would go and vary in your calculations, or in the hydraulic model study we'll talk about in a moment, you would go and vary your approach flows and estimate the captured flow depending upon the properties of your inlet and your slope and crossfall of the road. And when you look at these inlet capacity curves, generally there's 100% capture up until some point. Once you reach this point where you no longer get your 100% capture, you get this deviation off that you see here. Now it's not absolutely true, but the general trend is that the steeper your road, the less water you're going to catch in your on-grade pits. And that's because the velocity and momentum tends to carry the water past the inlet. So when you've got a much flatter roadway and you see you've got a 0.25% curve up here, you tend to capture a whole lot more water. When you get these curves, often they're given in curves like this, that you'll digitize. The other way you often will get the data is in the form of a polynomial equation. And through entry, you also inside 12D can enter these coefficients instead of digitizing these curves. So now I'd like to take this moment to say, well, how exactly do we get these curves into 12D model? So let's jump back to 12D once again. And I'm going to bring up that network the drainage.4d file editor one more time. And let's investigate farther down into what these on-grade inlet curves look like. So you'll notice here for this road pit that we have, we've got a set of 5 curves, all with the same road crossfall, 2.5%. And so that constitutes one set of crossfall measurements. And down below, we've got another set at 3.3% crossfall. And then within the crossfall sets, we've gone and varied the road grade. So let's just take a moment to take a look at this first road grade. Now down below below here, this part will look fairly familiar. This is the digitized points off those curves we were just looking at. Generally, your curves will start at 0, 0, and the next point will be your 100% capture. So it will be the end of the 100% capture. And then you start out with your approach flow, and you'll notice that we're no longer capturing 100% of the flow. So that's the data. Now let's go back and take a look at the name that we associate with this curve. The name that we assign it is generally an indication of how the tests or calculations were done. So in this case, it was felt that the calculations or the tests done will be valid for a 1% or 1 to 2% road grade and a 2.5% crossfall. There's two other numbers down below here now that probably need a little bit more explanation. Let's start with the crossfall. Because we have two sets of crossfalls, we need to decide when we will start using these sets. And our flattest crossfall is 2.5%. So we figure we should start using that set, no matter how flat it is, right down to 0. If we were to move down to the other set, which is the 3.5, you'll notice that the crossfall threshold is set at 2.9. Because 12D will select one of these curves, it will not interpolate between them. So essentially what happens is if the road grade comes up and hits 2.9, we'll switch over and start using this set of curves. Anything less than 2.9, we'll be using this set. Now the exact same philosophy is used for the road grades. So you'll see that these tests were thought they'd be accurate. It's time to start using them at 1%. But because we have a 1% and a 0.5%, we've decided in this case to switch over to this 1% grade curve when the road grade hits 0.75. So I hope it's clear just how exactly these threshold curves work. Threshold values for our curves work. I also mentioned that you can add an equation instead of digitizing the points. So now I'd just like to pop back to the drainage.4D editor to show you how that option works. So you don't want to enter both options, but if I was to come down here and I did want to add a inlet capacity curve, I'd go to this child selection tool and add the inlet capacity equation. And inside the inlet capacity equation, I could enter in the 4 polynomials as I showed in that earlier screen. The multiplier simply takes the total inlet capacity and multiplies it by that factor. So generally your multiplier will be 1. So now that we've talked about the background, at least for the on-grade pits, let's take a look at the steps that are required to make inlet capacities enabled inside 12D model. So going back to 12D model, let's head across to our global tab. And on the global tab, we have our utility model tab where we link up the 12D drainage network to the other models inside 12D. And this is the model here that's going to make it all work. Now this training webinar is not about bypass flow strings, which indeed would take up another webinar and it'd be a very interesting one as well. I look forward to that. But right now we'll say that we just need those bypass flow string models specified in order to get our bypass running. And what these bypass flow strings do is they're just a string going from one inlet to the next inlet to say this is where the water goes when it will not enter. So once we've got that model in there, the next thing that happens is when we go to do an analysis, we need to make sure we have the consider bypass flows selected. Now that's a crucial when we do our rational method 1D surface flows and when we do our dynamic 1D. That tick box is not required when we do the 2D analysis. So those are the 2 bits to remember, is that if you want to do bypass flows, make sure that's turned on and make sure that you've got your bypass flow models for the 1D and the rational and dynamic. Well, after talking about those pieces and ready to go, let's review this. I've talked a great deal about the road grade and road crossfall, but let's see how we get that data into our 12D model. So once again, I've gone and selected that first inlet up here. Let's head back to the pit tab. And if we move back down to our bypass, you'll notice that there is a road grade and road crossfall. Now, if I was to turn on the manual tick boxes, I'd be welcome to put in my own values if I wished. The concept of the Drainage Network Editor when it was designed was that you can go 100% manual if you wish, type in the values, or the way that most people will use it is an automated procedure where 12D will calculate the values for you. So let's try going the automatic method and start taking a look at this. Now that I've shown you the manual, we're going to switch over to that automatic. In order to get the 12D model to automatically calculate the road grade and road crossfall from your data train model, we're going to need to use our road strings. Now these road strings are used for several different aspects of our hydraulics and our physical layout of the model. Essentially, they're not required, but this is one of the options inside 12D, just keeps giving. It's like every time you look at another part of 12D drainage, you find out there's one more thing you can do with our road design strings. So in this case, what we're going to do is focus on looking at these last three columns and how they impact the measurement of the road grade and road crossfall. So you'll notice that they're completely blank right now, which means we're going to be using the default values. Now there's a few extra rules in the defaults, but essentially we will move up one manhole diameter in the uphill direction and in order to measure the road grade. Now of course we want the road grade of the approach flows, and that's why we've gone uphill. And when we go uphill according to the data train model. So officially these set-out strings only need to be an XY string at this moment. So by moving upstream, we're going to take two measurements off the data train model in order to measure the road grade. And those distances are taken at the distance apart at this slope measurement distance. Now if you leave that blank once again, it goes to the default, which is 1/10 of the manhole diameter, and there's minimums to that. And that's how we determine the length. So now we've got a length, we've got 2 points, we can determine a grade. All of that comes because we have a road set-out string. If we're interested in a road crossfall, which is not necessarily required, we need to have a road centerline string. And this is so that 12D will know which direction from the set-out string to go in order to measure the crossfall. We certainly do not want to measure the crossfall out here in the footpath. So that's what we can see with our magenta string, and what we've done again is come out a manhole diameter towards the center line of the road and measure the crossfall. Now, once again, if you feel that you have a better idea about what these distances should be, you could override them by putting into the road design file. So let's go take a look at live for a moment where that would happen. So there's our global tab, there's our utility models. If we go and open up that road design file, okay, you'll see that we have the road grades, the road crossfall, the slope measurements. We've got our set-out strings, which we will use to determine the road grade, and we've got our centerline strings so we know which way to go measure the road crossfall. Now on a small technicality, you only really need the road crossfall if you have more than one set of crossfalls. If you have a single set, well, there's no need for the extra one because your choice is limited to one set. So that's just a little bit of the background information about how you can automatically calculate the road grade and the road crossfall for an on-grade inlet. Now let's take a look at these inlet capacity curves that you would have entered and a way to display them to yourself and probably someone who's going to review your design. Back inside 12D, we have an option under Design Drainage Sewer. We have to go all the way down to More, and it's called Write Inlet Curves to Model. Now when I do this, I tend to put a Z at the beginning just to make sure these models appear at the bottom of my model list. We multiply the numbers by 1,000. I didn't mention it before, but all of the data that we were entering into the drainage.4D file was in cubic meters per second because we're operating in the metric system. So multiplying them by 1,000 in this case would convert the cubic meters per second into liters per second and convert the meter depths into millimeter depths. So when we go run that, it's a very quick routine to run, it goes and creates a new set of curves. Now often I'll set up a view just ready for my inlet curves, and on this view I've got my Don't need those axes. I've got my axes for my approach flow. Let me move that across. And my captured flow. And I've got my inlet capacity curves for my road pit. Now, a fair question would be, where did those axes labels come from? If you're interested in putting those on your drawing for when you show someone, of course they're not required, but those are available in a 12DA file inside our library, and I'll show you that name shortly. So what we're looking at here is the data that we looked at in the drainage.4D file. If you remember, that was the end of the 100% capture. So if I was to click on that, you'll notice that that was, let me get a point snap. That was the 1616 from the lowest curve, okay? So that's our end, and then we have, of course, all the extra points from our curves. So, excellent idea to print these curves so you know exactly what you're using inside your design. Let's leave the on-grade curves behind, and let's move over to talk about the inlet capacity curves for a SAG. Now, sag pits, once again, as I mentioned, is where the water generally will stop at a location, of course not come to complete stop, but not bypass, and then start flowing into the inlet. So it will pond up. So it's the depth above the grate that becomes important. So now we'll take a look how we can enter this depth versus Q in. Now, if you do get an inlet capacity curve from many sources, there's a tradition inside the stormwater industry to put the flow depth on the vertical axis. And this comes about because the depth, of course, is a vertical measurement, and hence the vertical axis seemed to be a good idea. 12D has gone more with the scientific consistent approach, where we put the flow, inlet flow, on the vertical axis again, exactly the same as the on-grade pits, and we put the depth on the horizontal axis. So let's just go back now, jump into 12D and see where all that happens. So the very first thing I'll do is I'll go back and I might turn off those curves, and I'm going to add on some sag curves. So what I'm going to do is put on my axis labels, and then I'm going to come down here and add on my cap curve sag for my road pit. And let's add those on. So once again, this becomes the x-axis. You notice it's depth this time, so it's been a little bit flipped. And one thing I'd like to bring to your attention is that if we looked at about 150 millimeters of depth, this is a typical 2-meter side entry pit, we're capturing almost 300 liters per second. So once again, keep in mind that sag pits tend to capture a lot of water. Now that's what the curve looked like. I haven't showed you what that curve looked like inside the drainage.4D file, so if I just pop back there one more time, go back to that user, let's just pop down to the sag inlet and go take a look at the sag inlet curve. And once again, there's your depth versus your Q in. The depth in millimeters and your Q in cubic meters per second. One thing you might have noticed with a sag curve is you have only one. On grade curves, of course, you have many. On a sag curve, there's a single curve for that. Now, in this configuration, these inlets are only used either in a on grade or a sag, and not both. However, that's not always the case. Many times a user will have a stormwater inlet that can be used equally well in a sag location and in a on grade location. In that case, we would ask you to put both sets of curves inside one manhole type, and then you would definitely not specify this value here, because you'd want to leave that open to the user to decide at modeling time whether it was going to be in a sag location or an on-grade location. Now let's go back, and just as we did for the on-grade inlets, I'd like to go back and talk about how we get the depth measurements for the different hydraulic methods inside 12D. So let's start with the rational method. So moving across here to a plan view, and let's just get that out of the way. What 12D does is we need to know what the maximum ponding depth is before the water starts to flow out of this catchment and over into the neighboring area. If you've gone and drawn your catchment strings inside 12D, and it's a sag pit, you would expect this catchment line to be drawn around the crest of the catchment. And so all the water flows from this crest line down to the inlet. Now, if we were quick enough and we were going to go and drape that catchment strings onto your design tin, now just for those who aren't familiar with that, the design tin is the one specified in Global Main. Okay, so if we drape these onto the design tin, and 12D does that automatically, it will find the low point. Now the low point on the crest is when the water will overtop. So what 12D needs to do is to find out the elevation of that low point, find out the elevation of the grate, and the difference will become the ponding depth. Now the place we're going to find that ponding depth, once again, is on the pit bypass. And if I was to go select that sag inlet, you'll see that down here, we still have the other ones, but they're grayed out. But because it's a sag pit, we have our maximum ponding depth. So once again, that was determined by finding the low point on the catchment string and subtracting the grate level. Now, the moment we specify our global utility models bypass and do a set pit details, 12D goes and creates a new model for us. And that new model is called construction drainage data. And it's an excellent one for helping us confirm how our inlet capacity calcs are being done. So I don't know if you can quite see it, and you probably can't. It's just a very small cross here. That is where the low point on the curve is, on the catchment strings. So if I was to go select that, there's my catchment, there. That's my network labels. And you can see I'm clicking here, and on myself, I'm not quite finding it. Let's just try that one more time. Catchment. All right, so when you have this moment, when it's a little bit tough to find them, the best way to get an accurate location of where these inlets are is if we go to our models, we can go down to our string information table and bring up the construction drainage data model. Now, if I sort them by the user points, I think I'm onto my trouble right now. I think this might just be a really great time to go do a set pit details for this. And let's go update that. All right, so these are the spill crests that I'm looking for. Now this was inlet C2, so there C2 is there. And when I click on it, you'll notice that there's a great big cross there that helps me accurately find that location. Now if I was to come back and ask for some more detail, I could hit my F2 key, which is my string inquire, and go and pick that location. And there's my construction drainage data point, and the Z value on that is 30.066. So that's the low point. That's the elevation when water will just start to overtop. Now the other thing, if I'm looking at just those, if I was to come back to my, I've got my minimum, and because there is only one point, the Z value specified there is also going to be the same Z value. Now if we head back to the pit and we take a look at this maximum ponding depth, there may be times when you may want to make that slightly deeper because you have an estimate of how deep the water is going to get when it overflows, or because your data train model isn't quite finished. It would be a good time that you might want to go manual and override that. One of the symptoms that your catchment strings are not quite in the right direction, or your data train model isn't quite up to scratch just yet, is that you'll get a negative ponding depth. We'd give you a warning if this ever happened, but what the trouble is, of course, is that if the overflow point is lower than the grate, then no water is ever going to pond up, and you're never going to capture any water. So watch out for those negative ponding depths. It means there's a bit of a data entry error on your model. So hopefully that talks a great deal about how we measure that maximum ponding depth for the rational method. Moving on to the 1D dynamic. The reason we had to enter a ponding depth for the rational method is it deals only in peak discharges. It has no concept for volumes or how much water it would take to fill up this area in order to bypass. That's not true with our 1D dynamic. It works with volumes, and it's an important part of the analysis. So I'm going to switch over to another model here that I have, which is my setup for my 1D dynamic. And let's go select one of those inlets. Same location. And what we do with the dynamic is, because with the dynamic we have dual hydraulic grade lines, we need to have a shape for what the overflow point is going to look like. And our plan here is to model this as an overflow weir. So when you're working in the dynamic, what I would be doing is going across to my pit tab and going to my bypass shape and selecting a string that I've drawn, just a 2D string, that goes along the crest. And then what that does is 12D automatically drapes that onto your DTM and gets the shape of what it looks like when the water overtops that. Selecting in a road weir tells 12D to model the overflow as a weir type calculation rather than a conduit. Now, whenever 12D drainage works with a shape of a conduit, we're always using shapes, and the absolute elevation, or RL, will come from somewhere else. So when you do this, what we need to specify is what that low overflow point is. And the place that happens is on the bypass tab, and it's the same number you saw before with the rational method, 30.066. So essentially what that does, if I do a right mouse click and maximize this, you'll see that the bottom elevation, okay, of our channel shape is sitting at 30.066, and that's when the water would start bypassing. So what's going to determine the bypass is when there's enough volume to fill up this area, and then it flows over. So you'll see it's done slightly different inside the 1D dynamic. And when you do the 1D dynamic, the pit maximum ponding depth is no longer relevant or used. Let's now just take a look at what happens in a 2D dynamic model. When it comes to the 2D dynamic model, we have to decide what sort of connection mode there is between the node and the 2D domain. So if I pop back once again, grab my drainage network editor, and I was to pick one of my inlets, head to my pit tab, and you'll notice that the connection is determined. 12D will automatically do this via the grate. So whenever the water is going to enter the stormwater inlet via the grate, we will do inlet capacity calculations. And if I was to hit, because it's marked once again as a sag pit, we would do sag pit in calculations. One of the things that 12D will do automatically is it will connect all of the outlets to the sump. Because of course the water is not going to bubble up and come out of it. Well, it might for a bubble up pit. But if I was to come down and to pick this outlet here, oops, network editor, go back and pick that outlet, and head to the pit tab, you'd see 12D would automatically have connected that to the sump. So the concept there is that the water is going to exit at the bottom of the stormwater inlet. So you can see the water would be coming out down here and entering directly into the 2D domain. So it's important that your 2D connection be set correctly. Now, the other time you want it connected to the sump is when you're doing a culvert. So if you happen to have any of the culvert inlets set, it will change the KU method. And if 12D sees the KU method being any one of our culverts, then it will also switch this over to be a sump for you. So to summarize that once again, if you have an outlet or a culvert, 12D will automatically hook it up to the sump. If you have it hooked up to the, everything else winds up being a grate, unless of course it's a manhole. And with a manhole, there is no connection. On the selection menu, you'll notice there is two different options, a not set versus a none. Well, the difference here is that if we go to the not set, it means on the next run, 12D is more than welcome to go and change it to whatever it feels is appropriate. So not set means instructs 12D to go and select one of these. If you select it to none, That's a way to tell 12D that you absolutely under no circumstances want that inlet connected to the 2D domain. So you'll see that's the extra step when it comes to looking at inlet capacities and the connection between the 1D pipe system and the 2D above ground analysis. Now there's going to be one other step that comes into the connection, and that is to make sure that the cells are big enough to deliver the water to the inlets. Now when I talked about a sag pit, we talked about the fact that they do capture a great deal of water. And in the analysis that we're about to run when we're all finished here, we're using 1 meter grid cells. Now a 1 meter cell may not have enough water, probably won't, to supply a sag pit. And also the lintel is often 2 meters or longer. So in order to do this, we need to instruct 12D to connect more than one grid cell to the sag inlet. And we do this via 2D connection zone lines. So the idea is inside 12D is you draw a string cutting across the inlet, the cells that you'd like to connect, and then finish off at the center of the inlet. When we look at the line that the cells that these line crosses, this line here, that determines. This last little bit, the last segment, is completely ignored in the selection of the cells. So if we were to jump back into 12D for a moment and just to see what one of those would look like live, okay, there's the line that's drawn there. And if I went to my global tab, get back over there, let me just go pick that one so we'll stay a little bit in that area. There we go. So if I go to my global tab and utility models, that's where I've specified the model containing those connection zones. And it's the set pit details button that tells it to do the connections. So in short, when you're doing the 2D modeling and you feel that your inlets need to be connected to more than one cell, this is exactly what you need. You need a connection zones model and those connection zone strings. Now, just before I take you back to the PowerPoint, the actual inlet calculations, the depth of water on the surface is something that 2Flow has a good handle on. It reports back to 12D exactly what the depth is, and then 12D extracts that amount of water from the 2D domain and passes it into the pipe system. And of course, that exchange could go in either direction if we had excess flow coming up to the surface. So that's about the 2D connections and the connection zones. One question that frequently comes up is, well, what about trench grates? What about these long grates that their inlet capacity is dependent upon their length? One of the methods that I've seen our users use is to, the inlet capacity for these is specified in cubic meters per second per meter of grate. So what I might recommend is to enter that inlet capacity as a fixed value into our drainage.4d file. And then what happens is you can use your inlet efficiency to specify the length of the grate. So for example, if you were to put in a 2 meter long grate, it would take this number and multiply it by 2, and then it would change the inlet capacity. A good way to look at trench grates. Currently there is a maximum of 10 allowed for inlet efficiencies. So currently, without doing some other fudging, you'd have to keep your grate lengths under 10 meters. So we've talked a great deal about the setting up of the inlet capacities. And in case you're wondering, yes, we are going to do live runs at the end here. But what I want to do before I move there is to talk a little bit about inlet efficiency and blockage. Now, if we remember those original pictures where the water was freely flowing into the grates in that hydraulics lab, just how a stormwater inlet blocks is wide open. There are so many different ways that an inlet could block at the upstream, the downstream, it could be the side. So what happens when we start looking at blockage? The question really is how will the stormwater network perform under reduced inlet capacities? Now that's a very open-ended statement, reduced inlet capacities. And there's two primary ways I've seen people model or want to model the reduced inlet capacity. And what I have labeled here is option A, and this is one that's often talked about in the early versions of AR and R, where you will go and multiply the captured flow by an inlet efficiency. So for example, 0.8. So what happens in this case is that all of this axis gets multiplied by 0.8 and it essentially flattens out the curve. Now, if I was to jump back into 12D just for a moment and go take a look at those inlet curves, then I might just flat jump back to my on-grade ones. Okay. What that's going to do, it's going to move down this axis. So before, when I was capturing 16 liters per second, if I had an inlet efficiency of 0.8, it would bring that down to 80% of that. So, but the trouble is it's not just this point. If I had 1 liter per second approaching, I would only capture 0.8 of a liter per second. And that really doesn't work very well if you're trying to model 100% inlet capacity. So another good idea came out for multiplying inlet efficiency, modeling reduced inlet capacities, because keep in mind that's what we're trying to do, and that was to multiply both axes by a factor. Now this has a much more interesting effect. What happens is the 100% inlet capacity point moves directly down the line. So we go back into 12D, okay, that's 16. Okay, would move straight down here until we get to the 80% mark. But so the 100% inlet capacity would end at a lower value, but we would still get 100% inlet capacity. So the effect of this is to take this entire inlet capacity curves and to scale them down. So we've adopted the name scaled inlet capacities. So if I went to my global tab and to main, 12D has an option of scaled blockages, and you can use that for the 1D or the 2D analysis. It's currently not available for the rational method. So that's the concept, is it scales down the entire curves by multiplying both axes by that inlet efficiency. And that's just a screen of how we do that. Now, the next part of inlet efficiency is how we put these values in when we're ready to look at a major storm. Inside 12D, we work with the concept of defaults, where you can set implicitly what the inlet capacities are. So defaults pits, and this is if we take a look at the major storm, we've set the inlet efficiencies to 0.8 for our on-grade pits, and we set them to 0.5 for our sag pits. Now, anything that you ever find on the defaults tab, you're always welcome to override that and explicitly set it. So if I went back to my pit tab and then went back to the bypass, I'd be able to specify my inlet efficiencies there. And of course, blank means use the default, and if you happen to have forgotten what the default is, it'll be presented to you as the tooltip. So that's what we're going to look at doing for the inlet efficiencies. So, great deal of information has been presented here, and we've gone through and talked about the on-grade pits in both, on-grade sag and manholes, and we've talked about them in all three modeling, the unsteady, the 2D model, and the rational method. So now what I'd like to do is to go run these and take a look at the results. So what I'm going to do is jump back into 12D, and let's start with the 2D modeling. So with our 2D modeling, the first place most people are going to get access to this is by using the road flow. So I come across here and grab our road flow. You'll notice that this has been pre-filled out, and that's because I have set the defaults. Save myself a little bit of typing during the presentation. Now, it's not a road flow webinar. As a matter of fact, we have a very good road flow webinar on our YouTube site. But the part I want to draw your attention to here is that on the optional tab, we've definitely gone and specified our drainage network. And it is that drainage network that's going to be supplying the flows to that model, which is why we have our rainfall on grid set to 0. So when we go and hit that run button and say, yes, we'd like to start up, it's going to erase the files, start from scratch, and it's going to analyze every one of those inlets that's within the 2D domain and mark them as a grade inlet connection or a sump inlet connection or none, as we discussed earlier. 2D modeling is this one is being run on a 1 meter grid, and you will notice that it takes a moment or two to run. And as we do have a race to run this afternoon, I don't think we'll wait till this is entirely finished, but I would like to make sure that I get up to the peak flows, and it is a 25-minute storm. So once I get past this 25-minute threshold, Maybe we'll go a few extra minutes in the runtime. I think we've pretty well got it. You can see that the wet cells are dropping off, so the system is definitely in the recession limbs. We can just finish that. And now that that's finished, we'd like to go read those results in. And when we read results, we always need to pick the log file, and we can go read those results. Now, if we jump across, I've got a view already set up with our tins on it. And of course, one of the beauties of 2D modeling is you can see here we've got our approach flow to this pit. As soon as the water starts to go around the corner, you'll notice that it doesn't follow directly around the corner. We get to see the effect of the velocity and momentum of the flow. And of course, we've got a very large catchment coming down this direction, which is why we get that extra momentum carrying the flow over in this direction, and then off it goes and it continues down the roadway. So the 2D gives us a very good idea of exactly where the water is going to go. But now let's jump back and see how we can look at those results. Once again, we'll jump to the Drainage Network Editor, and I'll start out by taking a look at this on-grade pit we're looking at earlier. So if we head across to our Results tab, one of the graphs that's available with our 2D, or our 1D as well, is our approach flow, elevation, and captured flow. So I'll hit the Enter key on that, and I'll maximize this so that everyone can see it quite clearly. Now this gives you a good snapshot of what's happening. We've got 45 liters per second approaching from our catchment flow. We're capturing 40 liters per second, and almost 5 to 6 liters per second is bypassing on the downstream side. So at the same time, we can take a look at this vertical axis, and this brown axis refers to the brown line. So it looks like we've got about 40 mils of depth as the water approaches. Now keep in mind, for an on-grade pit, it's the approach flow that determines how much going in. I was just mentioning the depth part. So if we were now to jump down and take a look at that sag pit and go back and ask for that same graph, we would get a completely different graph. And because this is a sag pit, we got 600 liters per second approaching here. What's determining how much gets captured is the depth. And you can see the depth has gone up to 300 millimeters. Now, if you remember back to the other models, especially the rational, when we talked about 121 as the maximum ponding depth, well, this means that the overflow that's overflowing the road is up to a good 100 millimeters deep, or even, of course, 180 if you click on the math. So it's the depth here, once again, that's determining. Now, the inlet flows. The other thing that's odd is you'll notice the capture flow all of a sudden takes a dive right about the peak of the storm. Bit of bad timing, if you ask me. But if that happened, I'd certainly want to investigate why. So let's go back and let's ask for our grade and invert elevations. And what you're going to see here is that the subsurface HGL went and reached the grade level. And as soon as that subsurface reaches the grade, of course, that's going to inhibit how much water can capture and come back down into the subsystem. Not only that, as soon as the two HGLs meet together, the surface HGL provides a much greater head to push water through the pipe. So that's going to accelerate the outflow from a pipe, and then vice versa, it's going to decrease the flow in the upstream pipe. So that joining of the subsurface and the surface HGL is a critical analysis, or a very, very important part of the analysis that 12D does. And of course, you can see the impact of that on the inlet capture. So that gives you an idea of the inlet capacity when we run our 2D models. Now let's step across and take a look at a 1D model. So if I go grab the same Drainage Network Editor and I go pick a 1D, now this is a 1D dynamic, okay? So if we go and do exactly the same thing as we would have done, we'll go run that. And this time we've definitely made sure that we have considered bypass turned on. It's going to run a 1D analysis. Now when we do the 1D analysis, the difference there is that the storage and the volume at this location is determined by the overland flow routes that come in. So those overland flow shapes determine, let's get down back here to the SAG, how much storage is available at the SAG. But essentially the same philosophy. I'd come back to the results. I could ask for my approach flow and elevations, and I'd get very similar results for the 1D dynamic and the 2D versus the approach flow when captured, as you would expect. They won't be exactly the same because the modeling is slightly different, but they will be close. And the same thing would be true if we came back and picked the sag locations and we asked to see the depths and the captured flows here. So once again, very similar, but not exactly the same. The last method, of course, we talked about would be the rational method. Now keep in mind that the rational method does not do any hydraulic calculations on the surface. So when we come back and run the analysis for the rational method, okay, the best place to take a look, of course, we've got our bypass flows on the surfaces here, labels. If we go to our drafting, go to multi-string translate, and make sure we have our text snap on, the group option is a great way just to pick these labels up and move them more a little bit easier to read. So you see we definitely have our approach flows, because we're using the rational method, are about 100 liters per second in this case. Keep in mind there's been no calibration or tried to make them the same. They are lower, so we'd expect to see our inflows and our bypasses slightly less. So we've covered a great deal inside that webinar. We've talked about all of our inlet capacities for our on-grade, our sag, and our manholes. And now what I'd like to do is to turn ourselves back over to Lisa and to see if we have any questions from our listeners.
Thanks, Rob. We had a few questions through. I'm just a bit conscious of the time, and I'll just read out just one of these here. So Philip in New South Wales was asking, does 12D consider ponding volumes at SAGs or only the volume in the bypass conduit?
Does 12D consider ponding volumes at SAGs or only the volume of the bypass conduit? Well, yes, we definitely include the volumes at the SAGs whenever we're doing 1D or 2D dynamic analysis, because those are the two that have volumes associated with the hydrographs and have volumes in the surface. So when we do our 1D, what we do is we look at the approach overland flow shapes, and we look at the volume that's inside those. So at every node, we take 1/2 the length of the approach channel, and then we take a look at the cross-sectional area at the depth, and that determines the volume that's available. So yes is definitely the answer to those ones. And then you also had that word though, or only the volume in the bypass conduit. So yeah, keep in mind that the bypass conduits include the ones that are leaving, but also the ones that are approaching. So yes, so it's not only, but we do take care of all the volume that's there. If for some reason you wanted to add additional volume to that, and there might be a reason that you thought that would be more appropriate, you'd be more than welcome to go add additional volume from a basin curve. And usually that would only be done if you had a great deal of volume at some very high levels. But that's something you definitely could.
Thanks for that, Rob. I think we won't push our luck with technology any further today with questions. We'll get back to everyone else by email. The recording of this webinar will be available in coming days through our website and our YouTube channel. If you need to contact us in the meantime, you can visit our websites. That concludes our presentation for today. Thank you everyone for attending, and we hope to see you at future webinars.